The protective shield of our planet decays and eventually fails. So do our satellites. First, communication satellites in the highest orbits go down. Next, astronauts in low Earth orbit can no longer contact their mission control center. And finally, hazardous, relentless cosmic rays start bombarding everything on Earth, causing havoc and devastation. Are these the terrifying consequences of the planet's magnetic field reversal we're going to face? Right now, as you're watching this video, Earth's north magnetic pole is extremely out of whack. It's so serious that scientists will have to update the global magnetic field model released a mere 4 years ago. Does it all mean that the magnetic pole of our planet will flip soon? Be patient. We'll figure it out a bit later. You see, the magnetic pole is moving quite erratically from the Canadian Arctic towards Siberia. And these movements are very unpredictable, but it's normal for the pole to be moving. There are long-term records from London and Paris that prove that the North Magnetic Pole moves randomly around the rotational North Pole over periods of several hundred years. But the most astonishing thing about its movement is that it's speeding up. Around the mid-1990s, the magnetic pole unexpectedly accelerated from a bit over 9 miles to 34 miles a year, and recently, the pole crossed the international dateline, moving toward the Eastern Hemisphere. The European Space Agency launched extremely accurate magnetic field satellites in 2013. Thanks to them, researchers have superb data they can use not only to make magnetic field maps, but also to update them every 6 to 12 months. That's how they were able to notice that the core field was weakening too. It might be a sign that the planet's magnetic field is about to flip. To understand this process better, we need to figure out how the core field works. Let's say we've got a bar magnet that runs through the center of our planet and has a north and a south pole. This magnet is incredibly strong, representing about 75% of the intensity of our planet's magnetic field at the surface. Our bar magnet is not only moving but also getting weaker by about 7% every century. Admittedly, this bar isn't the perfect representation of the core field. It's more like electric currents generating Earth's magnetic field. Still, this model makes it easier to see what's happening to our planet now. The magnetic field of our planet plays an important role in protecting us from dangerous radiation and geomagnetic activity, which is the product of the interaction between the solar wind and Earth's magnetosphere. Earth's magnetic field also moves. Scientists have been studying and tracking the movement of the magnetic poles for hundreds of years. The historical motions of these poles indicate changes in the global geometry of the magnetic field of our planet. And they may point to the beginning of the field reversal too. That's what a flip between the north and south magnetic poles is sometimes called. You see, if the north magnetic pole moves a bit, it isn't a big deal. But a complete reversal might have a serious impact on the climate of our planet, as well as modern technology. Luckily, such flips don't happen overnight. The entire process stretches over thousands of years. Plus, even though the magnetic pole weakens during a pole reversal, it doesn't disappear completely. So, those scary events from the beginning of the video aren't likely to happen to us. The magnetosphere will continue protecting the planet from cosmic rays and charged solar particles, even though there might be some amount of particulate radiation that will make it to Earth's surface. Magnetic fields are generated by moving electric charges. If some material allows these charges to easily move in it, it's called a conductor. Metal is a great conductor, and we often use it to transfer electric currents from one place to another. In this case, the electric current is negative charges called electrons moving through the metal. The current is what generates a magnetic field. Earth has a liquid iron core. In other words, there are layers and layers of conducting material inside our planet. Currents of charges are constantly moving throughout the core, and the liquid metal is also moving and circulating there, generating the magnetic field. This magnetic field, in turn, produces something resembling a bubble around the planet. It's called the magnetosphere, and it's located above the uppermost part of the atmosphere. This layer shields and deflects high-energy cosmic ray radiation, which, otherwise, would be extremely hazardous to people and other forms of life on Earth. The magnetosphere also interacts with the ionosphere, the layer of our planet's atmosphere containing loads of ions and free electrons, and capable of reflecting radio waves. The interaction between these two layers and magnetized solar winds is what scientists call space weather. The solar wind is normally mild, and there's no space weather whatsoever. But sometimes, the sun starts shedding gargantuan magnetized clouds of gas that can accelerate to incredible speeds. They are called coronal mass ejections, CMEs. They are ejected from the sun over the course of several hours. CMEs usually look like giant twisted ropes and can occur spontaneously. Their frequency varies according to the 11-year-long solar cycle. For example, at a solar minimum, you can observe one ejection per day, and when the sun is in its most active phase, there might be 3 CMEs per day. Coronal mass ejections disrupt the calm flow of the solar wind and cause serious disturbances that can damage stuff both in space, near Earth, like satellites, and on the planet's surface. If coronal mass ejections make it to Earth, their interaction with the magnetosphere generates geomagnetic storms. Those can trigger auroras, happening when a stream of energized particles hits the atmosphere and lights up. And then there are also solar flares. They develop more rapidly and with much more energy than coronal mass ejections. Solar flares often occur soon after coronal mass ejections. The most powerful volcanic eruptions pale in comparison to solar flares that release 10 million times more energy. Within a few minutes, one solar flare can give out billions of tons of charged particles. Solar flares are also insanely hot, with the temperatures reaching several million degrees F. Astronomers believe that such bursts of solar radiation happen when the sun's magnetic field gets twisted in some regions. At one moment, all the pent-up energy is released. The star sends out light and particles, mostly electrons and protons. Most solar flares last for minutes, but some continue for hours. A powerful solar storm can potentially cause a devastating global blackout on Earth. If not for Earth's magnetosphere, the effects of the sun's activity would be much more devastating. Luckily, the magnetosphere deflects most of the solar material hurtling toward our planet from our star at a speed of over 1 million miles per hour. But even so, during space weather events, there's a lot of hazardous radiation near Earth. It can potentially harm astronauts and spacecraft. Plus, space weather can damage large conducting systems, for example, pipelines and power grids, by overloading currents running inside them. Scientists regularly map and track the overall orientation and shape of our planet's magnetic field. To do it, they use local measurements of the field's orientation and magnitude. That's why they have been able to conclude that the location of the North Magnetic Pole has moved by almost 600 miles since the first measurements were taken in 1831. The magnetic field of our planet reverses on a timescale varying between 100,000 to 1 million years. One can tell how often it happens by looking at volcanic rocks at the bottom of the ocean. They capture the orientation and strength of Earth's magnetic field at the time of their creation. So, dating those rocks gives us a good picture of how our planet's magnetic field has evolved over time. From a geologic point of view, field reversals happen quite fast, but they are extremely slow from a human perspective. A complete reversal normally takes a couple of thousand years, but during this time, the orientation of the magnetosphere may shift, exposing more of Earth to cosmic radiation. Hundreds of millions of rocks orbit the Sun within the asteroid belt between Mars and Jupiter. but only some of them come relatively close to Earth. NASA classifies asteroids orbiting within 48 million kilometers of our planet as near-Earth objects, NEOs. And inside this group, there are particularly worrisome objects. Those are so large and orbit so closely to our home planet that they could turn into a real threat to the world should a direct collision occur. At the moment, NASA is keeping a close eye on an asteroid named Bennu. It's a fairly large space object, 610 FT across, that might smash into our planet in 159 years. According to experts, the asteroid, which was first spotted in 1999, is quite likely to drift into the orbit of our planet. If it happens, it might collide with Earth by the 24th of September, 2182. Asteroid Bennu is thought to be taller than the Empire State Building. If it hits our planet, the collision will release 1,200 megatons of energy. That's an enormous amount of energy that nothing built on Earth could produce. Scientists from NASA believe that, during the flyby in the 22nd century, there is a tiny chance that the asteroid will pass through a gravitational keyhole. That's a region of space that might set the space traveler on a certain path, which could result in the asteroid crashing into Earth. Bennu flies by our planet every 6 years. It has had 3 close encounters with Earth, in 1999, 2005, and 2011. These days, scientists estimate the chance of the asteroid hitting our planet by 2182 as 1 in 2,700. That's more than 5 times a person's chance of being struck by lightning. But even though Bennu's chances of colliding with Earth are quite low at the moment, the space rock has still been categorized as a potentially hazardous asteroid, all because it might come as close as 7.5 million kilometers from Earth. That's the reason why it's also classified as a near-Earth object. Bennu is a carbon-rich asteroid that formed in the first 10 million years of the history of the solar system. That's around 4.5 billion years ago. No wonder this space body holds precious clues to the origin and development of the rocky planets of our solar system, which are Mercury, Venus, Earth, and Mars. Even better, it may contain organic molecules similar to those that are crucial for life to evolve. In 2020, NASA's OSIRIS-REx, Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer managed to briefly touch the surface of the asteroid. It collected some sample space rock afterward. For NASA, it was the first mission of this kind, but it won't probably come as a surprise that Bennu isn't the only asteroid we should worry about. Asteroid 99942 is another space body we'd better watch out for. It's a near-Earth object about 335 meters across. It was discovered in 2004, and at first, it was identified as one of the most dangerous asteroids ever detected. Apophis gained notoriety very fast. It was believed to pose a serious threat to Earth. Experts predicted that it would come uncomfortably close to our planet in 2029. Luckily, after a more careful examination of Apophis and its orbit, astronomers concluded that there was no risk of the asteroid colliding with our planet for at least a century. The risk of an impact in 2029 was ruled out completely, as well as the potential impact that could be caused by the asteroid's close approach in 2036. Interestingly, until March 2021, there was still a small chance of a collision in 2068. But then, Apophis made a flyby of Earth, and astronomers took this chance to use powerful radars to estimate the asteroid's orbit around the Sun more precisely. This allowed them to rule out any impact risk for at least the next 100 years. Now, the reason why such discoveries make us so worried is that even a relatively small asteroid, the size of a house, can wreak havoc upon colliding with our planet. And if an asteroid is larger than 1 kilometer across, astronomers call it a planet destroyer. The impact energy released by such an asteroid after striking Earth could be devastating. That's why knowing where such asteroids are and in what direction they are moving is crucial. The problem is that our capability to protect the planet from asteroid impacts is not top-notch yet. If such a catastrophe was about to occur, we would need pretty much time to prepare, because an asteroid collision is no joke. Probably the most well-known asteroid impact site is the Chicxulub crater. It's the evidence of the terrifying collision that led to the extinction of dinosaurs. Strangely, this crater isn't very visible, but some others are. For example, Barringer Crater in Arizona, which is also called Meteor Crater. It looks rather blood-chilling when you think about the collision that led to its appearance. In any case, we now know that space rocks hit not only Earth, but also the Moon, Mercury, and Mars. No rocky planet in the solar system is safe from asteroid impacts. That's why we have an entire scientific enterprise whose goal is to find and catalog the asteroid population of the solar system. It might sound a bit scary, but there are around 25,000 asteroids larger than 140 meters in diameter near the orbit of our planet. Such a space rock is large enough to wipe an entire city off the face of the Earth. So far, less than 50% of such asteroids have been detected and tracked. There are also an estimated 230,000 objects equal to or larger than 49 meters in size. Those are capable of destroying a concentrated urban area. And still, fewer than 8% of those have been detected. There are also tens of millions of smaller, near-Earth objects. They are larger than 10 meters across and might cause some surface damage. Less than 1% of such small space bodies have been discovered so far. The thing is, the inner solar system is extremely challenging for asteroid search. Each night, there are only two 10-minute windows when astronomers can observe the region, all because the sun's glare creates a very bright background glow. Plus, the atmosphere of our planet also distorts and blurs observations. Spotting asteroids in such conditions is beyond the capabilities of most telescopes. A really unique instrument is needed to fulfill this task, and the tool of choice is the Dark Energy Camera, DEC, at Cerro Tololo Inter-American Observatory in Chile. This device wasn't designed to hunt asteroids. Researchers built it to search for another elusive target, dark energy, the mysterious force driving the expansion of the universe. The DEC is supposed to observe hundreds of millions of galaxies. That's why it's both wide and deep. This way, it can both peer deep into the universe and capture a wide field of view, which helps it record the motions of galaxies and the conditions in the early age of the universe. But it also means that the DEC is perfectly suited to spotting asteroids near the Sun. Inner asteroids are rare, and deep images are necessary because such asteroids are faint. Scientists need to be able to fight both the bright twilight sky near our star and the distorting effect of Earth's atmosphere. And the DEC can help them achieve their goal. The Dark Energy Camera was built to carry out the Dark Energy Survey, which finished in 2019. Now, astronomers can direct the power of the camera toward other tasks. They claim that the DEC survey is one of the most sensitive searches ever performed for objects near Venus's orbit and within the orbit of our planet. It provides us a great chance to find out what kinds of objects are lurking in the inner solar system. Well, we've been miscalling Uranus all this time. Astronomers say we should be pronouncing it like urine-ass, not Uranus. I can't say a different stress changes much though. However, things could have been different. Initially, Uranus was supposed to have the majestic, king-like name of George, because astronomers wanted to name it after King George III. In the end, they changed their minds, and now it's the punchline of every joke. If you take the total cost of launching a mission and divide it by the weight of the cargo, you'll see some pretty mind-blowing figures. According to specialists, back in 2016, it used to cost $10,000 to send just 1 pound of cargo into space. But now, prices have gone through the roof. Cygnus spacecraft's cargo costs over $43,000, while SpaceX's new carriers come in at around $27,000 per pound. Remember how hard it is to pay $5 for water at airports. Now, a bottle of water in space would cost somewhere between $9,100 and $43,000, and that's only to have it delivered in space. As for water in space, well, it used to be considered a super rare thing, but in reality, there's water ice all over our solar system, so you don't have to buy those overpriced 43K water bottles. It's hanging out in comets, asteroids, and even in hard-to-see craters on Mercury and the Moon. We're not sure if there's enough water in these places to support colonies of people, though. Mars also has ice at its poles, hiding under its surface dust and frost. Even smaller celestial bodies, like Saturn's moon Enceladus and dwarf planet Ceres, have ice. NASA scientists think there might be a chance of finding life on Jupiter's moon Europa. There may be liquid water beneath its icy shell. Europa, even though it's a lot smaller than Earth, might have an ocean deep enough to hold twice as much water as all the oceans on our planet combined. And in 2009, scientists exploring a massive cloud of gas and dust in the center of our galaxy stumbled upon a fascinating surprise. They found ethyl format within the cloud. This chemical is responsible for the delightful flavor of raspberries and has a rum-like scent. Furthermore, another nearby region is brimming with ethyl alcohol, the same type found in many beverages. In fact, there is enough alcohol in this region to provide every person on Earth with 300,000 pints of beer every day for the next billion years. But believe it or not, but we do have a black hole on Earth. The thing is, creating an in-lab black hole was a sorta indispensable thing to do. Studying black holes in real space remains a distant dream, so it was only possible to create one to experiment with in a lab. A group of scientists in the Netherlands wanted to explore the mysterious Hawking radiation theory proposed by the iconic Stephen Hawking. Using atoms to mimic an event horizon, they orchestrated electrons, causing a surge in temperature that resembled flat space-time. As particles moved through quantum fluctuations, a ring of infrared radiation appeared around the lab-grown black hole, mirroring Hawking's idea. Grown black hole, mirroring Hawking's idea. It may sound insane, but you can totally be allergic to the moon. Long story short, it was the final Apollo mission, and they brought back more rock samples than ever before. Plus, they had the first and only pro-scientist on the moon, Jack Schmitt. He was a geologist, and his rock samples helped scientists learn more about the moon's magnetic field and volcanic history. During the expeditions, it became evident that Jack Schmitt was allergic to moon dust. The gritty, sticky powder clung to his suit and his skin, causing irritation in his sinuses, nose, eyes, and throat for a couple of hours after he took his helmet off. Neutron stars are extremely dense, being basically just a bunch of neutrons squished into a super small space. If you had just a teaspoonful of this stuff, it would weigh more than the entire human population combined. And to match the density of a neutron star, we'd all have to squeeze into a space the size of a sugar cube. No thanks. And when it comes to outer space, we tend to think that Earth and the Moon are pretty close together, but in reality, you could actually squeeze all the other planets of our solar system between Earth and the Moon. The average distance between them is about 384,000 kilometers. If you added up the diameters of the 7 planets, you'd still have some room to spare, about 8,000 kilometers. In 2011, scientists made a groundbreaking discovery of a massive reservoir of water in space. This water, equivalent to 140 trillion times all the water in Earth's oceans, could provide each person on our planet with a planet's worth of water 20,000 times over. This reservoir was located near a massive black hole, drawing in matter and emitting energy, known as a quasar. The water was formed by energy waves colliding hydrogen and oxygen atoms together, and it was found around 12 billion light-years away. When Curiosity Mars rover snapped its very first sunset pic in 2015, scientists were practically doing backflips from excitement. Turns out, sunsets on the red planet are anything but red. they're actually a stunning shade of blue. According to NASA, the reason behind this phenomenon is that the dust in Mars's atmosphere is like a magical filter that lets blue light shine through while blocking out those warm tones like yellow, orange, and red. Venus is a slow spinner compared to Earth. It takes this planet 243 days to make a full rotation, and it spins in the opposite direction. But even though Venus takes longer to spin around, it zooms around the sun in just 225 days because it's located so close. So, believe it or not, a year on Venus is actually shorter than its day. I chose 12. You might think that the night sky should be full of stars with no dark spaces at all. This idea is known as Olbers' paradox, named after German astronomer Heinrich Wilhelm Olbers. He thought that if the universe was infinite, unchanging, and timeless, then we should see stars everywhere we look. But it turns out that the universe is not infinite, unchanging, or timeless. Edwin Hubble discovered that the universe is actually expanding, and the leftover radiation from the Big Bang tells us that the universe is about 13.8 billion years old. Think of all the birthday candles. So, the reason we don't see stars in every direction is because some stars are just too far away, or they haven't been around long enough for their light to travel all the way to us. During the Apollo 16 lunar mission, Ken Mattingly, the command module pilot, had a bit of a scare when he realized his wedding ring was missing. The whole crew frantically searched the spacecraft for it, but no luck. Finally, on day 9, while Mattingly was on a spacewalk, the ring was spotted floating out the hatch door. Charles Duke Jr. tried to grab it, but missed. Luckily, it bounced off Mattingly's helmet into Duke's hands. It's cool they found the ring, but there are many other things people left up there. There's even a toothbrush floating around somewhere. Mercury is already the tiniest planet in our solar system, not counting Pluto, of course, and the second densest after Earth, and believe it or not, it's actually shrinking and getting denser. For a long time, scientists thought Earth was the only planet with tectonic activity, but that all changed when the Messenger spacecraft flew by Mercury, giving us a detailed scan of the whole planet. In 2016, Messenger discovered these cool cliff-like formations called fault scarps. Since they're still relatively small, scientists think they're pretty new, suggesting that Mercury is still contracting 4.5 billion years after the solar system began. Around 10 years ago, Italian astronaut Luca Parmitano went through a near-drowning experience during his spacewalk due to a water leak that went unaddressed. Nobody knew how it happened and why Luca ended up having water in his helmet. NASA was investigating the issue for months, but they were unable to determine the exact cause of the water entering Luca's helmet. NASA sent a spacecraft right into the sun. It's the fastest human-made object ever, 692,017 kilometers per hour, and could cover the distance from Philadelphia to Washington, D.C., 139 mi, in just 1 second. The Parker Solar Probe's mission is to study our star's dangerous behavior. Scientists warn that massive solar storms are inevitable, and the consequences could be catastrophic for our planet. The spacecraft got 7 times closer to the sun than any other probe ever did, 6.1 million kilometers to the sun. It managed to do so during its 20-second flyby to the star since its launch in 2018. Because our star is so massive, 333,000 times heavier than Earth, its gravity is really strong, like a giant magnet. As the probe flies around the sun, it uses gravity to go faster and faster, and eventually picks up that crazy speed. As it got closer and closer to the sun's corona, which is its outer atmosphere, the probe had to survive temperatures of 1,400 degrees Celsius. That's hot enough to melt many metals. It was protected from that heat and radiation by a 11 centimeters thick carbon shield. It kept the tools inside the probe safe and running at around room temperature. The scientists went to all this effort because they're hoping to solve a big mystery about the sun that's been puzzling them for ages. The surface of our main star is already super hot, by 5,537 degrees Celsius, but as you move further out to the corona, the temperature shoots up to millions of degrees. And it doesn't make any sense because it's farther away from the sun. So maybe we could finally get some answers about this heat phenomenon. The mission is also going to help us understand something called solar wind. The sun is constantly shooting out tiny bits of energy and charged particles into space, like a never-ending breeze of electricity. When this solar wind hits Earth, it can create amazing light shows in the sky called auroras. The more active the sun is, the farther south you can see auroras. Our star follows natural cycles that last about 11 years. The activity goes from low to high and back down to low. Right now, we're in the solar maximum, the peak of the activity cycle. That's why we've spotted beautiful auroras in the most unexpected places in 2024. The downside to it is that the sun's activity can send out bursts of energy and charge particles that can mess up things like radios, satellites, and even GPS. It can be dangerous, especially for astronauts out in space who aren't as protected as we are here on Earth. Humans wouldn't feel the compression of the planet's electromagnetic field because of all the extra radiation, but power grids are really sensitive to it. If we don't act fast when it happens, the influx of energy will go into power transformers all around the world, disrupt them, and leave big areas without electricity. If this happens during a hurricane or a tornado, when communication is already super important, it could make it much harder for emergency services to communicate and save lives. That's why it's so important to learn to predict this space weather. It's tricky because, unlike most disasters, like earthquakes, floods, or volcanoes, it doesn't leave behind any kind of physical evidence. The only big solar storms we really know about happened in 1859 and 1921. The first one, called the Carrington event, was so wild that it made sparks fly from telegraph wires. The auroras were seen all the way near the equator. Scientists back then were using a special kind of paper that reacted to light to record solar activity. During the Carrington event, the reading from the sun went off the page. Literally. Whatever was happening, it was so extreme that we still don't fully understand it. Then, there was the New York Railroad storm of 1921. It was powerful enough to knock out telegraph systems across the US, Europe, and the Southern Hemisphere. The storm boosted radio transmissions for a bit, making them travel farther than usual. But back then, there weren't nearly as many radios, so it wasn't super helpful. The bigger problem was the electrical grid in the US, which was heavily damaged. Back in 1859 and 1921, people weren't as dependent on tech as we are now. If a storm like that hits today, the consequences could be way more catastrophic. Scientists from New Zealand who study space weather are working on simulations trying to prevent disasters from happening. They say one of the possible options to do it is to study other suns like ours elsewhere in space. If we get data from thousands of stars, not just one, the picture for analysis would be more complete. So far, scientists have launched or plan to launch several other missions in addition to the Parker Solar Probe, the GOES-19 satellite, 2024, ESA's Solar Orbiter, 2020, the Space Weather Follow-On Satellite, 2025. Meanwhile, NASA is working on another mission, launching Endurance, robotic moon machinery on steroids. Its main mission will be to collect samples from key lunar locations that will later be retrieved by astronauts from the Artemis program. These samples are spread across the largest impact basin on the moon, South Pole Aitken Basin, over 1,931 kilometers across, separated by hundreds of miles. To do it, Endurance will have to be way more advanced than Perseverance, NASA's current most cutting-edge rover. Endurance will drive roughly 100 times further, drive 10 times faster, and collect roughly 200 times more sample mass. Endurance would also be the first planetary rover to drive at night, and because it will be on the far side of the moon with limited communication to Earth and surface data, it will have to drive autonomously between sample locks and make its own decisions in tough conditions. When it reaches its destination, it's going to switch to a more classic way of doing things. Scientists back on Earth will get involved directly, guiding the rover to explore the sites and collect samples. The teams on Earth will also keep an eye on how the rover is doing by monitoring its telemetry, which is the data it sends back, like its health stats. If they spot any signs that a part is wearing out or something isn't working quite right, they'll tweak the plan to keep things running smoothly. All this will cost huge amounts of money, probably way more than the Viper moon mission that was canceled after NASA had spent around $450 million on it. While Endurance is in the planning stage, the Blue Ghost lunar lander is already on its way to the moon. Its main mission is research. It will spend 25 days in Earth's orbit, taking measurements and waiting for the right time to fling itself to the moon. After 4 days in transit, Blue Ghost will hang out in lunar orbit for another 16 days to collect more data. Then it will descend to one of the largest basins on the moon, Mare Crisium, and spend 1 lunar day, 14 Earth days there. It will measure subsurface thermal data, radiation levels, and other important data. At the end of its mission, Blue Ghost will take some final pictures of the lunar sunset. It isn't designed to return back to our planet, so when the night falls, it will do some final work and go offline for good. NASA chose the team of University of Florida aerospace engineers to work on another innovative space project, GRADIS, Gravitational Reference Advanced Technology Test in Space. It will cost $12 million, and its goal will be to improve the way we track changes in tectonic plates and oceans on Earth from space. It will use state-of-the-art sensors that will measure even the tiniest gravitational changes, monitor droughts, assess groundwater reserves, and better understand changes in sea levels. They expect to launch it around 2027 aboard a SpaceX Falcon 9 rocket. This year before September, a star in the constellation of Corona Borealis will explode, and in the northern hemisphere, we'll be able to see it with the unaided eye. This star is T Coronae Borealis, a white dwarf star 3,000 light-years away from our solar system. It will turn into a nova, which we'll discuss a bit later, in spring or summer. Even though this occurrence is predictable, happening every 80 years, it's still a once-in-a-lifetime event if you're a human. T Corona Borealis is not your regular star. It's actually a binary, 2 stars orbiting each other. This pair, though, is incredibly special. Occasionally, the stars increase their brightness to such an extent that they become visible on Earth. The white dwarf star is the more massive one of the two, but the most shocking thing about it is that it might pack the same mass as the Sun into a volume only as large as Earth. The companion star, an aging red giant, has already expanded so much that it's dumping its material onto the white dwarf. So, it's time for another explosion for these two. It's going to take the star's brightness from magnitude 11 to magnitude 2. In astronomy, magnitude is used to measure the brightness of a star or another celestial object. The brighter it is, the lower the number assigned as a magnitude is. In our case, it means that we'll be able to see the star with the unaided eye, even in light-polluted skies. Now we can only see the binary with binoculars in a completely dark sky. After the outburst, T Coronae Borealis will remain the brightest star in the constellation of Corona Borealis for a few days before gradually dimming. This event shouldn't be confused with a supernova. In a supernova, a star's core collapses, which leads to its complete destruction. It can only happen to a star 8 times the mass of the Sun. Instead of disappearing in a blinding flash of light forever, T Coronae Borealis will experience a nova, an explosion on its surface, flinging matter into space but not ruining the star itself. Such recurrent novas happen at regular intervals. T Coronae Borealis was known to astronomers of the past as the Blaze Star. Last time, it exploded in 1866 and 1946. Astronomers from NASA believe that it's going to do it again before September this year. The constellation of Corona Borealis, also known as the Northern Crown, is one of the most beautiful out there. It's a curved semicircle of 7 stars, which is easy to find in April. You should go outside 2 hours after dark and look to the east-northeast. Once you find the Big Dipper, use the curve of its handle to go arc to Arcturus, finding the bright star in the Bodas constellation due east. If you go diagonally down to the east-northeast horizon, you'll spot Corona Borealis. If you want to observe the brightening of T Coronii Borealis, it might be better if you get acquainted with the region and the stars of the constellation it's in. Once the event begins, you will be able to compare its brightness against the other stars and observe the thing without using any fancy cameras. A nova is a short-lived sudden explosion, involving a compact star as large as Earth or a bit bigger. The outburst comes from a white dwarf circling remarkably close to a regular star, so close that a stream of gas flows between them. This gas starts piling up until it creates a layer on the white dwarf's surface, and then it reaches a point where it detonates in a runaway thermonuclear explosion. According to astronomers, around 50 novae happen each year in our galaxy, but not all of them are noticed. NASA's Fermi Gamma Ray Space Telescope has observed several novae that occurred not far, on the scale of the universe. They found out that each blast produces gamma rays. Those are the most energetic forms of light. Researchers also think that these gamma rays result from collisions among numerous shock waves racing from the explosion site in a quickly expanding shell of debris. Now, after we've talked about novae, it's time to discuss something much more dramatic: supernovae. It's the largest explosion humans have ever seen. Each blast is a super powerful burst of a star. One kind of supernova is caused by the last hurrah of an extinguishing massive star. It happens to stars at least 5 times the mass of our Sun. Once they near the end of their lives, they go out with a ginormous bang. Huge stars burn incredible amounts of nuclear fuel at their cores, producing tons of energy. It makes their centers immensely hot. Heat generates pressure, and this pressure keeps such stars from collapsing. But any star is in balance between 2 opposite forces. Its gravity attempts to squeeze the star into a tiny, tight ball, and the nuclear fuel, burning in the core of the star, produces powerful outward pressure. Now, when a giant star is running out of fuel, it starts cooling off. Its pressure drops, and gravity wins. The star collapses. An enormous object that is millions of times the mass of Earth collapses within 15 seconds. No wonder this brisk process produces enormous shock waves. It makes the outer layers of the star explode. Eventually, an incredibly dense core is all that is left behind, besides a growing cloud of hot gas called a nebula. A black hole, the densest object in the universe, is the result of a supernova of a star around 10 times as massive as our Sun. There's another type of supernova. It usually happens in systems where 2 stars orbit each other, and at least one of these stars is a white dwarf the size of our planet. If such a star collides with another or pulls too much matter from its neighbor, it can explode into a supernova. Also, supernovae are often so bright they can outshine the combined light of entire galaxies for several days, or even months. Supernovae aren't common. Astronomers think just a few of them occur within a century in galaxies like our home Milky Way. But since the universe contains an enormous number of galaxies, we can observe a few hundred supernovae every year outside our galaxy. Unfortunately, space dust blocks our view of most supernovae happening within the Milky Way. Betelgeuse, a late-stage red giant, exploded in 2019, but it wasn't the event we expected to see. This star is found in the constellation of Orion and is huge, so big that if we moved it to the middle of our solar system, its outer edge would go way beyond the orbit of Jupiter. When Betelgeuse eventually nears its end, it will explode in a stunningly bright supernova visible on Earth even during the day. This explosion could happen as soon as tomorrow or as far-flung as hundreds of thousands of years from now, so don't hold your breath. But then, what was it in 2019? Astronomers noticed that the star was dimming. They decided it was the initial stages of the grand show, but instead, Betelgeuse went back to normal over the course of the next few months. Further analysis revealed that the star hadn't dimmed. It just looked like that because we had been observing it through a cloud of stellar debris. At the same time, the amount of light in the photosphere of Betelgeuse ramped up. It was like a massive explosion of material from the surface of the star. Events like this occur on the Sun all the time, especially when our star's activity is high. Bits of the Sun's surface get tangled up and cast off. That's what we call coronal mass ejections. They do not harm our planet, but they can mess with satellites and electrical equipment. Getting back to Betelgeuse, we've never seen such a huge mass ejection of the surface of a star before. It's a new phenomenon, which we can observe directly and even see surface details with the help of the Hubble telescope. Astronomers say we're watching stellar evolution as it happens for the first time. There's this mysterious thing in space, an unusual spot that scientists haven't been able to explain for more than 15 years. There are different theories, and one of them says that maybe this is an imprint from a collision with a parallel universe. Is this true? Well, let's see. Take a look at this map. This is the map of our universe. Well, not really. This is actually the map of cosmic microwave background radiation, or simply CMB. Many, many billions of years ago, there was a Big Bang. It was so powerful that it created our entire universe. And of course, such an event couldn't occur without leaving some consequences. And these consequences are literally everywhere. The Big Bang left electromagnetic radiation, which we know as CMB. We don't notice it in our daily lives, but it's literally here, under our noses. And if you had some kind of superhuman vision, you would see how everything around you shines with this dim light. This radiation is very important. If we hadn't discovered the CMB, we would have never found out about the Big Bang. Previously, scientists believed that the universe had always existed. There was no beginning and there won't be an end. It sounds pretty ridiculous to us now, but less than a century ago, people were absolutely sure of it. Stephen Hawking was one of the first scientists to guess that the universe did, in fact, have a beginning. The guy was so cool that he realized this as a student while working on his doctoral dissertation. But, unfortunately, he had no proof. If there was such a strong bang billions of years ago, then where are the traces? Where's the proof? Laughed people who believed in the eternal static universe theory. But don't worry, they had the proof rubbed in their faces real soon. In 1965, astronomers Arno Penzias and Robert Wilson discovered CMB, and that was the first grandiose proof of the Big Bang. It turned out that radiation was everywhere. We just didn't notice it. In fact, at first, Penzias and Wilson themselves mistook it for the noise of a big city, or pigeons, or something else. For their discovery, which turned the world of science upside down, they received the Nobel Prize. Alright, so people learned that they were surrounded by electromagnetic radiation. Then, they started collecting more data about it. They accumulated more and more info over the years until they made this very map. This is a map of CMB temperatures. But while creating it, scientists discovered something unusual. Let's take a look at this map. It looks like a large and diverse pattern of cold and warm places. But in reality, our universe is quite uniform. All temperatures on this map are close to 455 degrees with very little difference. All temperature fluctuations between these places are small, and each tiny speck actually spreads over millions of light years. So everything in our world is pretty calm and stable, except for one point. This cold spot right here. Astronomers first discovered it in 2004. First, it looked like nothing unusual. It's just a region where the temperature is below average for a couple of microkelvins. But remember, we're not talking about a small area. This is a giant cold region. It's literally billions of light years in size. Wait, the scientists thought, this can't be true. The universe should be consistent everywhere. According to our standard model, This cold spot simply shouldn't exist. But it does exist, though. This isn't just some mathematical error, it's right there. So, what is this cold spot and how did it appear? Astronomers have been trying to find the answers to these questions for years. Even now, we have only a few theories. So let's discuss them all. Theory 1, cosmic texture. This idea was brought up at the end of 2007. Then, scientists suggested that this cold spot could be the hills of space. In other words, it may be a bumpy region of the universe, just part of its texture. But that's a silly explanation, so this theory was quickly discarded. Theory 2, the supervoid. This hypothesis was considered the most plausible for a while. It stated that the cold spot was actually the so-called supervoid. It's a terrifying, dark place of our universe with almost no galaxies. And because it's an empty region with almost no stuff in there, it seems cold to us. However, this theory was refuted in May 2017. After carefully examining the cold spot, scientists found out that there were no signs of a supervoid there. Moreover, voids and supervoids, which actually exist by the way, are still very small in size. The cold spot is literally thousands of times bigger than them, so there must be some other explanation. And there is one, perhaps the most bizarre of them all. Theory 3, a parallel universe. This controversial idea was put forward by cosmologist and theoretical physicist Laura Mersini-Houghton. She suggested that the cold spot could be an imprint from the collision of our universe with a parallel one. Standard cosmology cannot explain such a giant cosmic hole, says Mersini-Houghton. This is the unmistakable imprint of another universe beyond the edge of our own. Her assumption is based on the theory of the multiverse. This theory says that there's actually an infinite number of universes like ours in the world. They constantly collide with each other, giving each other a push, which creates a new Big Bang. So maybe the cold spot is a bruise from such a collision? For quantum mechanics, such crazy theories are pretty common. But for standard physics and our simple understanding of the world, this is earth-shattering. Of course, we need strong evidence. And Mersini-Houghton's team has begun to work on it. Professor Tom Shanks from the Center for Extragalactic Astronomy at Durham University also participates in this research. The craziest sounding of the exotic models for the explanation of the cold spot, the multiverse is actually the most standard in terms of our current model of the universe, he wrote in one of his works. So, what evidence do we need? Well, our cold spot is located in the southern hemisphere. According to Shanks, if there really was a collision between two universes, we should find another cold spot, and it should be in the opposite northern hemisphere. If astronomers actually found it, this theory would be confirmed, and it had become the first proof of the existence of a parallel universe. But it's not that easy. To find a second spot, we need the latest, highly sensitive telescopes. We also need to find out some info about the nature of dark energy, how it affects space, and, in other words, there's still a lot of work to do. Not so long ago, scientists actually believed they had discovered the second spot. Researchers from New Mexico thought they had found it in the northern hemisphere. But unfortunately, this is likely to be a mistake. The map these researchers used had a high measure of randomness, so it's possible that their discovery is just an accident caused by other voids. So basically, we haven't found another cold spot so far despite careful analyses. But again, even the best modern equipment is not perfect, and it doesn't mean that there's no second spot. It just means that we haven't found it yet. But if one day we did find it, it could change the world of science forever. We'd confirm not only the theory of parallel universes, but also the famous string theory, and it could explain everything that occurs in our world. But if this happens, we'll get even more questions than we already have. How did these two universes collide? How does it all work? So far, it's all just guesswork. We can't claim that the cold spot is a print from the collision of parallel universes, but we can't refute this either. Actually, we may never know the truth at all, but it's still interesting to strive for it. The center of the Milky Way is a story of intense radiation, gravity, and mystery, a place where the forces of nature are pushed to their limits. But what if our own planet were to find itself in this cosmic theater? What would happen if the Earth were located there and somehow managed to survive? Let's start this journey to the heart of our galaxy and find out. Picture this. You're floating in space, surrounded by billions and billions of stars. Suddenly, you see a bright, swirling mass of gas and dust in the distance. That, my friend, is the Milky Way galaxy, our home in the vast expanse of the universe. The Milky Way is estimated to contain over 100 billion stars and is about 100,000 light-years across. In other words, if you were traveling at the speed of light, it would take you 100,000 years to cross the Milky Way from one end to the other. It's a couple trillions of miles. And it isn't just a static collection of stars and gas. It's a dynamic, evolving system. In fact, the Milky Way is currently hurtling through space at a speed of about 1.3 million miles per hour. One of the most fascinating things about our galaxy is its shape. The Milky Way is a spiral galaxy, which means that it kinda looks like a disk with a central bulge and spiral arms. The spiral arms are the areas where new stars are born. It's where the most stars, gas, and dust are concentrated. And this is where the solar system is located. Our system is like a tiny speck in the grand cosmic tapestry of the Milky Way. It's about 26,000 light-years away from the center of the galaxy, a pretty long distance, isn't it? The solar system is also moving through the Milky Way as it orbits around the galactic center. It takes about 230 million years for our system to make one complete orbit around the galaxy. Just imagine that. Since the time of the dinosaurs, we've traveled just a quarter of this way. The position of the solar system in the galaxy affects our life in many ways. For example, things like the amount of radiation and cosmic rays we're exposed to, and even the likelihood of asteroid impacts and so on. Also, thanks to our location, we can enjoy some pretty amazing views of the universe around us. From our vantage point in the Milky Way, we're able to see other galaxies, nebulae, and star clusters in breathtaking detail. We're also a part of a pretty happening neighborhood, with lots of other stars and planets nearby, so we're lucky fellows. But what would happen if we weren't so lucky? What if the Earth was located in the center of the Milky Way instead? The center of the Milky Way is home to a region of space called the central bulge. And it's just packed with stars. It's like a disco ball, but instead of shiny mirrors, it's covered in stars. Only this disco ball is really huge, about 10,000 light-years in diameter. The center of the Milky Way is also home to some extreme environments that would make even the bravest astronaut shiver. High-energy particles and intense magnetic fields can wreak havoc on electronics and spacecraft. Intense radiation fields can fry anything in their path, so it's not exactly a friendly place for life as we know it. So, if the Earth were located somewhere closer to the center of the Milky Way galaxy, it would be a very different place. Let's take a look at some of the potential effects. First of all, radiation. As we mentioned earlier, the center of the Milky Way is one of the most radiation-dense regions in the galaxy. It would make life on Earth very challenging, if not impossible. Sure, we have the Earth's magnetic field. It's like a giant shield that protects us from harmful radiation from outer space. But could it protect us if we were located in the center of the Milky Way? Unfortunately, the answer is no. It's kind of like trying to use a tiny umbrella to protect yourself from a massive storm. So it would be an easy win for the galaxy. But it's not all doom and gloom. There are some brave organisms that are able to adapt to high levels of radiation. We've seen that life on Earth has evolved to survive anywhere, from the depths of the ocean to the icy poles of the planet. So let's imagine what would happen if we somehow evolved to survive in these harsh conditions. Like, picture humans with tough, scaly skin that protects them from radiation and plants with unique structures that allow them to thrive in this bright environment. In that case, radiation still could have some seriously spooky effects on us. For example, it could damage DNA molecules and cause mutations. Imagine a world where plants grow with 5 leaves instead of 4, animals have strangely colored fur, or people have unusual eye colors or other unique features. And these are just some of the best examples. Let's not dive into the bad ones. Also, it could cause us to undergo some metabolic changes. Maybe our bodies could process food and other resources more quickly, which could lead to faster growth rates and larger sizes. Plants could grow tall and thick, and animals would be much larger than usual. There are also some organisms on Earth that are able to bioluminesce. Thanks to high levels of radiation, these organisms could potentially glow even brighter than usual. Imagine walking through a forest at night and seeing trees, mushrooms, and even insects glowing with an eerie blue or green light. Frightening and amazing, isn't it? But let's move on to the next big change: gravity. The gravity in the center of the Milky Way is incredibly strong, all thanks to a supermassive black hole, which is about 4 million times the mass of the Sun. This black hole is called Sagittarius A, and yep, it's our neighbor now. Great. And assuming we don't get swallowed by this black hole or crushed by this incredibly strong gravity, it still could trigger lots of earthquakes and volcanic eruptions. This black hole would be like the gravitational bully, pulling and tugging at everything in its path. Basically, if we survived this, we'd have an epic surfing competition every single day. Just add a bit of thrill of risking your life, and forget about running away from the planet. No easy rocket launches anymore. And physical objects won't be the only ones affected by gravity. Time would flow very differently for us. According to Einstein's theory of relativity, time passes more slowly in areas of high gravity. In other words, Earthlings would age more slowly than someone far away from the center of our galaxy. Also, the center of the Milky Way is a very busy place. Stars, planets, and other celestial objects moving around at incredibly high speeds there every day. The positions of stars and other objects would constantly be changing. In other words, say goodbye to normal navigation. The GPS systems would likely be unreliable due to the strong gravitational forces and high radiation. So if you accidentally got lost in a glow-in-the-dark forest with some creepy animals, good luck. But it's not all bad. The center is also home to molecular clouds. These are the regions of space where new stars are born. And the Milky Way in general has some pretty amazing sights to offer. For example, stunning nebulae like the Orion Nebula and the Eagle Nebula, which are visible with telescopes or even just a good pair of binoculars. So, if Earth were located in the center of the Milky Way, we would have a front row seat to some of the most spectacular cosmic events. Wouldn't that be awesome? Overall, if Earth were located in the center of the Milky Way, it would be a very different place. Of course, we all understand that our planet wouldn't have survived such a change, but it's still pretty interesting to imagine how our life would flow if we were there. And judging by what we just discussed, it wouldn't be pretty. So let's treasure and appreciate our small, quiet solar system.